All right, today we're going to talk about exponential and logarithmic functions. Only thing we're going to talk about today is graphing them. We're going to split this into two. We'll only talk about exponential today. You'll need a graphing calculator on these, so go ahead and get yours ready, and we'll begin on these. So what we need to understand about exponential functions are functions that have a variable in the exponent. So there are numerous families, infinite number of families for that matter, that are exponential functions. This is the 2-base function. We have 2 as a base value, and then we have a variable in the exponent. The fact that we have an exponent is not what makes a function exponential. Like this quadratic function does have an exponent, but the variable is not in the exponent. So if there is no variable in the exponent, it is not an exponential function. This is our doubling family. This is our tripling family. This is our quadrupling family, and you get the idea as we move through these things. So again, we're just going to take a look at our exponential. You notice the logarithms are written on the right there, but the logarithms we'll talk about tomorrow. So on our exponential function, what we have here is just plugging in the values. So a couple of things we want to remember. Remember, when we have a negative exponent, that is not the same thing as multiplying times a negative. What that means is the numbers that are in the numerator should be in the denominator, and the numbers in the denominator should be moved to the numerator. So I'm going to go ahead and plug in our first value. See, we have plugging in a -2 here, and we're plugging in -2 as an exponent to 2 to the -2 power. What this is saying is 1 over 2 squared, or 1/4. Now, I've taken these to my calculator. Hopefully you've got yours ready by now. And on this calculator, I've got these values put in already. So we're just going to graph these points as we see them. You see -3 is also in the graph there. -3 is like 1.125 right down there. -2 is at a quarter. -1 is at a half. So we barely can even see these moving. And then here's a point that I want everybody to highlight. That is 0, 1. That is kind of like on a quadratic, the origin. On a quadratic function, we always go through the origin. Well, on an exponential function, we always go through the value 0, 1. If we're not going through the value 0, 1, what that means is the function has been transformed. So we're going to graph a spot at 0, 1 there. Next thing we see is at 1, 2. And again, if you think about that, 2 to the 1 power, of course, is 2. And now we're going to start seeing that exponential growth. 2 squared is the 4th power, and then 3 is at 8. So 5, 6, 7, 5, 6, 7, 8. So we're there. So this is what our exponential function is going to look like. I'm going to zoom in real quick, because what we have happening is what's called an asymptote. It's going to run right through this line right there. And then now we start seeing that exponential growth, because at the beginning we are dealing with such small numbers that we're barely seeing any change happening there. But once we start getting to these integers, we see that the function starts flying. So this is what our exponential function, the doubling family, looks like. Go ahead and put these ordered pairs over here. 0.125, and again, resist the temptation to come in here and start putting in negative numbers. Those are not negative numbers. And then we will come back and look at the log base 2 is what that's called, but the log base 2 is the inverse function to this function. I want to talk about a couple of things while we're here. That is the domain and the range. The domain of this function is how far left and right that it's going. Well, we can see that it's going infinitely left, so it has a boundary of -infinity, and it's going actually infinitely right. So our domain is all real numbers. This is another spoiler for you. On an exponential function, the domain is always going to be all real numbers, just like quadratics. So if you have that, the domain is all real numbers. Now the range, on the other hand, is where we have some issues. We see that this range value, it is rising infinitely up and down, but it's hitting a wall when we get to the x-axis. So we have a range of values that will not get lower than 0. So that's our domain and range for the exponential function 2 to the x power. That's the doubling family. Another thing we need to recognize and point out on this, since our base value was a value greater than 1, we have exponential growth. Exponential growth. Exponential growth can go in both a positive and a negative fashion. Drawing another one, that's actually considered exponential growth as well. It's just exponential growth that's growing in a negative fashion. The way I like to think about exponential growth, it's either an airplane taking off or a submarine taking its dive as we move left to right. So this blue line that I have drawn, we can clearly see that's an example of a plane taking off. And then if I had the submarine diving, that's what that would look like. That's also an example of exponential growth. And the reason why we have the exponential growth is because of the value of 2, that base value that is greater than 1. So as we look at this one, we can see that our base value is equal to 1/2. When our base value is between the number 0 and 1, in other words, a fraction, then we have what's called exponential decay. And using the same examples as before, this would be the airplane landing or the submarine submerging. Both of those are kind of the end of their trip. Think of that. It's the decay of their trip. Their trip is now coming to an end. So we'll graph this one as well. We have a base value of 1/2. I just went straight to my calculator on this, but do understand that what we're essentially saying here is 1/2 to a negative 2 power. 1/2 to a negative 2 power. So let's take a look and see that the values that we have here. We have a value of -3, 8, -3, 1, 2, 3, 4, 8. We also have a value at -2, 4. We have a value at -1, 2. And of course, we have the value at 0, 1. We just talked about that. That is where it's going to hinge. If you look at that x equal to 0, if it's not at 1, you know you have some form of a transformation. And now we're about to see what a decay looks like. So we have a 1/2 value at 1. We have a 1/4 value, a 1/8 value, and then this is just going to slowly decay, half and half and half. So this is that asymptote that we saw earlier. It's getting closer and closer to this line, but it's never actually going to touch that line because we can't divide our way into being 0. So that number is going to keep getting smaller and smaller and smaller till it's incredibly insignificant, but it's never actually going to be 0. So we have another asymptote. That's called a vertical asymptote. So that's what our family of functions look like. Just like that. And again, you can see the log base 1/2 over there. That is this function's inverse. So it's going to resemble, but it's going to be an inverse function. So we've seen exponential growth. That's when the base value is greater than 1. I put an equal sign. Actually, when it's equal to 1, then nothing's happening. But if the base value is greater than 1, it is growth. If the base value is between 0 and 1, we have decay. And we have one other family. We have infinite number of families, but they're going to fall in one of three categories. It's the one that we just showed, the growth. It's the decay. And then we've got one more. We'll take a look at it real quick. All right, and the last little function that we're going to have here is the E button on your calculator. You can see I've highlighted that right here. It's the button right to the left of 7 and 4. If you hit second, and then that button, you have the E. That's Euler's number. What Euler's number is a number that calculates continuous compounding. Bacteria grow in this fashion. Bacteria don't wait for a certain time period to elapse. They are immediately, as soon as a bacteria reproduces, it is automatically a reproducing organism. This is called a continuous compound. It's continuous growth, either of those two things, and it's Euler's number. If you're curious what Euler's number is, all you need to do is take e to the 1 power, and you're going to see an irrational number. If you're curious, it's 2.73 something, something of that regards. Well, actually, we'll see it in just a second because we're plugging in those values. Now, this one is not even worth trying to plug these in by hand because it's a irrational number. Euler's number is. Let's take a look. Actually, I've got it right here. Here's what Euler's number is. It was close. 2.7183. I had my 3 and my 8 backwards there. So that's Euler's number. So what that's basically saying is he's calculated a continuous growing organism is just between doubling and tripling over time. So let's input our values here, and we're not even going to graph this one. We just want to get familiar with these numbers. But if I were to graph these, it would look like the one we did at the beginning, but it's basically between the doubling and tripling family. So here are our input values. -2 is 0.135. -1 is 0.3678. 0, of course, is 1. Even Euler's number has to follow that category. So that's actually where we'll start to look if we're trying to figure out transformations, which is where we're going to head next is transformations, how much we transform these things. One thing I want to point out, we're not doing it today, but one thing I do want to point out, ln, that's called natural log. Natural log is the inverse to Euler's number. Here's another thing I want you to point out on your calculator. Anytime you have a function on your calculator, like you see ln here, the second and that button is always the inverse of those things. Like if you look at the trig and you see sine, right above it is inverse sine. Any function that you have, the inverse is the second of that. So if you're working on your ACT, you can kind of use that as a cheat sheet. If you see a math that you're unfamiliar with, but you see the button, you can know to do the inverse of that by hitting second and then that button. All right, Euler's number is not really anything special except for that it has a specific purpose, but it's no different than the, sorry about that, it's no different than the doubling family or the tripling family. It's just specifically the number 2.7183, and that's repeated. It's like pi, it's an irrational number. But the graph is going to look similar to these two. It's just going to fall between the two. So tomorrow we'll take a look at our log-based stuff, and then we'll start transforming those things. The transformations, we've actually already studied these. We know how to move stuff left and right, up and down. We know how to stretch and compress them. It's going to be the same process with these. They just are shaped differently. All right, you've got a small assignment. Go ahead and get to work on that. Good luck.